Now, this part of the machine components design will be looking at flywheel and crank effort diagrams. Okay. So the introduction. Now, a flywheel is a mechanical device which uses the conversion of angular momentum. Okay, that is the product of I omega, which is the angular speed, to store rotational energy. Flywheel function is to store rotational energy, okay, in the form of kinetic energy, which is proportional to the product of its moment of inertia and the square of its rotational speed. So the kinetic energy for any rotating components, it is equals to half I omega squared, where I is the moment of inertia and omega is the rotational speed. Now, in particular, if we assume the flywheel's moment of inertia to be constant, okay, then the stored rotational energy is directly associated with the square of its rotational speed. So the amount of energy stored or delivered, okay, it totally depends on the square of omega. Okay, so because since rotational kinetic energy is half I omega squared, and since I is a constant for a particular flywheel, then the only changes refers to omega squared. So the kinetic energy, angular kinetic energy, or the kinetic energy will change with respect to its omega squared. So a flywheel used in machines serves as a reservoir, okay, which stores energy during the period when the supply of energy is more than the requirement. So especially when you refer to a four-stroke internal combustion engine, during the power stroke, okay, there will be excess energy. So this excess energy will cause the flywheel to rotate at a higher speed. So at the rest of the three strokes, that is the suction stroke, the discharge, and the compression stroke, all these require energy. So the energy which is in excess just now, which is stored during power stroke, will be given out to run out the rest of the three process. That means the three strokes. Okay. So, and releases it during the period when the requirement of energy is more than the supply. Okay, so supply energy is more during power stroke, supply energy is less and it requires energy from the flywheel is during suction, during compression, and during discharge, okay, strokes. So what happens is when there is excess, this flywheel here will rotate at higher speed. Okay, so the angular kinetic energy will be stored in the flywheel, okay, as it rotates faster. So it will releases the energy when there is a need of energy during other strokes. Okay, then the flywheel will rotate slower and slower by stages according to the engine requirements. So based on that, we have what we call a turning moment diagram. Turning moment diagram is taking T, that is the torque, as the y-axis, and the angle turn, the crank angle theta, to be the x-axis, okay, which is also known as a crank effort diagram. It is the graphical representation of turning moment or crank effort for various positions of the crank. It is plotted on Cartesian coordinates in which the turning moment is taken as the turning moment is taken as the ordinate of, sorry, here there is a slight, okay, y-axis. This should be y-axis, and the crank angle should be the x-axis. Okay, to be the x-axis, the crank angle, and the turning moment to be the y-axis. So we call it as t against theta diagram. And we know that, okay, for rotational objects or for rotational components, the work done is measured based on the product of t and theta, where t is the turning moment and theta is the angular displacement. T is the top, theta would be the angular displacement. So you can see there is a fluctuation of energy or work done here. So since work done is equals to the product t theta, so the area of the t theta diagram is actually equals to the work done per revolution if you are measuring it based on one revolution. So any areas that is being shaded here would represent the amount of energy that is required by the engine, okay, or to be delivered to the engine. Okay, so you can see this represents the fluctuation of energy from minimum to maximum, and then so on for one cycle of the rotation of the flywheel. So the shaded portion actually represents the work done or the kinetic or the angular kinetic energy. Okay, so anything that is above this mean resisting top line, we call this as the mean resisting top line. Any area which is above is considered as excess energy. Any area which is below the T mean line is considered as required, that means shortage. So it requires a flywheel to releases the energy to run the process. And this one, especially if let's say you are referring to power stroke, okay, so you have energy excess, and this excess energy will be stored in the flywheel and it tends to rotate at higher speed. Okay. So since the work done is the product of turning moment and angle turn, therefore the area of the turning moment diagram represents the work done per revolution. In actual practice, the engine is assumed to work against the mean resisting torque. So in actual practice, okay, the energy that is required by the engine, in actual practice, the energy that is required by the engine is usually measured, okay, by taking the area which is below the mean torque line. So area below the mean torque line is actually, okay, in actual practice is the energy required by the engine. So I have two diagrams here, 1 and 2. This is based on energy supplied, okay, or developed by the engine. Okay, so the area which I've shaded represents energy which is being developed by the engine. And the area which is under the mean resisting torque line would be the amount of energy that is required by the engine to run the processes. So when you overlap both the diagram, you will be able to get something as I've shown you here, which you can see area which is below and area which is above. So below, usually area below here, okay, means, okay, I use a simple words, that is shortage of energy. So the flywheel will tend to release energy in terms of kinetic energy to the engine. So what happens? It tends to rotate slower. So we call it as deceleration. So when you refer to B to C, when you can see this area which is above the top line, represents actually the energy is in excess. So what happens is the flywheel will rotate faster when there is an energy excess. So it causes the flywheel to accelerate. So here it decelerates and here it accelerates. So usually we use sign convention of negative for any area which is below the mean top and positive for any area which is above. So therefore, when you look at this diagram, this area should be considered negative. This should be positive energy. This should be negative. And this part here should be positive. So in actual practice, you can equate both of this, okay, to actually find out the mean resisting torque. You can actually equate both of these areas in order to find out the mean resisting torque, okay? So the turning moment is positive when the engine torque is more than the mean resisting torque. When the engine torque is more than the mean resisting torque. Then the turning moment would be negative when the engine torque is less than the mean resisting torque. So T, we use a symbol T here for the torque on the crankshaft at any instant, the torque transmitted. T mean as the mean resisting torque. Remember, always energy required by engine is always measured by referring to the area which is below the mean torque line. So then accelerating torque on the rotating parts of the engine. So if let's say you take T minus T mean, you get positive value, then it means acceleration. If you take T minus T mean and you get a negative value, then it represents that the flywheel would be decelerating. So according to Newton's second law, remember we can equate the T net, that means T minus T mean, to be equals to the product of I alpha. That's Newton's second law for rotational object. For linear straight line, we have MA, net force equals to MA. For rotational object, we have net torque equals to the product of I alpha, where I is the moment of inertia, which is measured in kg meter square, and alpha would be the angular acceleration, which is measured in radian per second square. So if T minus T mean, that's what I have explained here. If it's positive, that means the flywheel accelerates. If the T minus T mean here is negative, then the flywheel, we say it is decelerating or retarding. So this is a simple diagram which shows you there are areas that is shaded. This is called the mean torque line. This would be your mean torque line. So you can see area which is shaded above, below, above, below, above, below, and above. So remember, this we consider positive A, this we will consider negative B area, and this we will consider as positive C area, negative D area, positive E area, negative, and positive. And remember, the area of this represents the energy. Okay, area of T diagram represents work done on energy, okay, which is stored, which is developed, or which is required by the engine. Now, from this, okay, if let's say, for example, we want to find the greatest fluctuation of energy. So you see, the energy here actually fluctuates. So in order to find the greatest fluctuation of energy, usually we consider energy based on the T theta diagram, section by section, point after point. Okay, so let's say consider point A first. That means we are measuring the energy based on T theta diagram. So there are steps. So the steps that I'm showing you here, we are measuring it from point to point. So at point A, let's say we just give it an amount of, let's say, unknown amount of energy, which is in U joules. And amount, let's say it can be 10,000, it can be 20,000, it can be 30,000, 100,000 of joules of energy at the beginning, okay, of the flywheel. Okay, so when it moves to point B, then you will take this U here, which is the unknown energy, plus this A. Okay, then when you move to point C, then you will have this U plus A minus B. Then when you move to point D, then you have this U, which is at A, plus this A here, minus B, plus C. Then minus D at point E, and then plus E at point F, minus F at point G, and plus G at point H. In steps, yeah? Point after point you consider. So I've shown you here energy in the flywheel at point B. We have the U plus the A amount of energy. Then energy in the flywheel at point C, then you can see I have minus B. Then energy at point E, you can see I have plus, okay, C, this one. And then E minus D. And then F plus E. And then at G minus F. And then at H plus G, okay? So at the end, usually the end of the diagram, usually it will show you the remainder energy which is in the flywheel, which is equals to the initial amount of energy, most of the case, okay? It will go back to what you have initially, because we consider the energy balance stating that whatever energy is required by the engine, which is the area below the mean top, is equals to the energy developed by the engine, which is equivalent to the area under the wavy curve that I've shown you here. So when you equate both, so that means the equilibrium or the balance, when you start A with U, at the end you should get U. That means if you consider 10,000, at the end you should get 10,000 in most cases. So after that, we can find out the greatest fluctuation of energy by taking the maximum. So you have to see which one would be the maximum. Here we are unable to see because they are all without a value. That means without numbers. Okay. So what we do is usually to find the greatest fluctuation of energy, we choose from this list from point A to point H. What is the maximum energy which is developed minus the minimum kinetic energy? So you have to compare which one is the maximum and which one is the minimum. So when maximum minus minimum, you will get your greatest fluctuation. Next will be what we call coefficient fluctuation of energy. We use a symbol here for our study. We use symbol of beta to represent this term here. And this is defined as the greatest fluctuation of energy which we have just now. That is maximum kinetic energy minus minimum kinetic energy divided by work done per revolution. So that is W. Okay. So in other words, when you move your W towards the left, you will have the product of beta W, which is also representing greatest fluctuation in energy. So since we know that beta W is equals to maximum minus minimum, that is the greatest fluctuation of energy. And we know that, okay, maximum kinetic energy we can find by taking half I omega squared. Remember, angular kinetic energy is equals to half I omega squared. I is the moment of inertia, which is measured in kg meter square, and omega is the angular speed, which is measured in radians per second. So this will give you the maximum kinetic energy, and this will give you the minimum kinetic energy. That is based on maximum speed and minimum speed. At the beginning of the lesson, we have said I would be a constant. So it's totally relying on the angular speed power 2. So I is constant. So you have beta W would be equals to this. Okay. Or you can simplify this or expand. You got this. Okay. So in order to simplify, you have max plus mean, okay, divided by 2. If you take maximum and speed plus minimum speed divided by 2, actually you get the average or the mean speed. So that also can represent 2 times mean speed. maximum minus minimum, okay, divided by mean speed actually will give you the variation in speed. So actually, when you look at this, okay, you can simplify this and you get, you get your beta W is equals to I, which is the moment of inertia, phi, which we're going to define afterward, which is the coefficient of fluctuation of speed. Beta is fluctuation of energy, and phi is the coefficient fluctuation of speed. And this would be your mean speed squared. So the next we go to this symbol here, which is called the coefficient fluctuation of speed. So this is defined as the variation in speed over mean speed. The variation in speed is actually maximum speed minus minimum speed. That means the greatest speed minus the minimum speed divided by the mean speed. So here I have written down variation in speed, what it is, and then what is mean speed. Okay, so from this you will have maximum plus minimum actually is equal to 2 times mean. So that is why you have this here. Okay, and then the variation in speed is max minus mean. Okay, so max minus mean is actually your variation in speed. Okay, so therefore is equals to 5 times mean speed. So you see variation in speed is equal to 5 times mean speed, which is also equals to max minus mean. So it's equals to this part here. Okay, so that is how you got this formula. This formula usually we use in finding maybe the I, sometimes maybe the coefficient of fluctuation of speed, or sometimes even the beta W, that is the greatest fluctuation of energy. So this is the basic theory for flywheel and the crank effort diagram. So thank you for listening to my explanation and see you all in the next lesson.